Okay gentlemen, good morning. Welcome to the NTI-OSC Centre again. This is the second unit in the mandatory training modules and flange integrity. Okay, so welcome to the centre. We're not expecting any fire drills today, so if you hear the fire alarm, please stay with me and I'll escort you to the muster place. Today we are talking about flange integrity. I am Mathew. I'm the process and mechanical instructor, and these are the subjects we'll be looking at this morning. So a little bit on safety, types of flanges, jointing and gaskets, bolts and studs, bolting sequences, bolting methods and tools. Now, flange integrity or incorrect flange integrity has been one of the biggest causes of process accidents in the process industry for the last 30 years. It's very important, and it's very important that the people who are carrying out flange procedures are trained in their job correctly, and that's what today's all about. This is a cut down version of a course designed by the Energy Institute, which is the governing body which looks after the assets in the North Sea. Okay, now when you think about it, here we've got a flange, okay? We get the flange welded to the pipe. This is a weld neck flange, and we prep the pipe, we prep the flange, we prep them to 37.5 degrees each side. That makes 75 degrees. We get the welder to weld it. He has to be tested. It has to be inspected by an insurance assessor or NDT to a very high standard, and then we let anybody do up the flange with no training. It's completely crazy. Where is it most likely to leak? And the answer is obvious, isn't it? On the joint surface. It's never going to leak on the weld, is it? So this is what today's all about. Okay, now a bolted flange joint, it appears simple and uncomplicated, however there is a lot of science involved, of which we'll just briefly touch on today. Now the improvements have been driven by the UK HSE, the ECITB, national and international standards, and as a direct result of incidents over the years. There was the Piper Alpha disaster. You could say it is related to flange integrity. A PSV was removed, a blanking flange was fitted, and it wasn't torqued up correctly, and that was one of the main causes of the accident. There were other factors included in it. There was 2 different permits on different sides of the rig, and other factors, but one of the contributing factors was incorrect flange integrity. So, the definitions of today, I've spent a lifetime of talking about a gasket being a joint. For the purposes of today, a gasket is a gasket, and a joint is the entire thing, the flanges, the gasket, the nuts, the bolts, everything. And the authorised operator is clearly the technician or the responsible person in charge of tightening up the flange. Okay, now, what we shouldn't be using is these things, flogging spanners. I believe you guys call them a hammer wrench. These should only be used for untightening, never for tightening. A hammer wrench, as the name suggests, or a flogging spanner, is designed to be hit with a hammer. We've got no control over the amount of power we are putting into that fastening by using one of these things. These are terrible things, have been the cause of no end of accidents over the years. If you see your colleagues using these, please don't use them. Please tell them. Please near miss them. We should always use a torque wrench and the correct flange integrity procedures. A torque wrench ensures that everybody delivers the same amount of torque into that fastening. We should never ever use one of these things. Only for untightening or using as a backing spanner. Okay. Now, what's wrong with this then? We look at this flange. This has been tightened up in the field. Yep, that's right. There should be 2 to 3 threads of clear thread protruding from the nut. We can have more. It's fine to have more. It doesn't affect the integrity of the joint, but over time that stud will corrode, the painters will come and paint it, and it'll be difficult to remove next time. The optimum amount of threads hanging over from the nut should be 2 to 3 threads, like that. Okay, so an incorrectly bolted flange can produce a weak flange. If we follow the correct flange integrity procedures, we are 99% certain that that flange will never ever leak. Okay, now there are hazards involved. Obviously, if we incorrectly bolt the joints, there's potential for bolts to shear during breakout. The bolts can neck if we apply too much torque to them and eventually break. We can distort the flanges if we don't make sure they're parallel or don't follow the correct procedure. And we can also get pipe spring when bolts are released. We need to take this into consideration. We always need to be careful when removing the last fastening that the pipe isn't under tension or the line isn't under tension. If you misalign pipework that's directly connected to pumps, that can cause pumps to fail, the bearings to fail very, very quickly. Okay, now types of flanges. We're just going to briefly touch on the main ones today, and they would be ring type joint or RTJ, raised face, flat face, or male and female facings found on heat exchangers. It's very important you don't get types of flange faces and types of flange fittings mixed up. We're just talking about the facings that you'll come across today. Okay, now this is a ring type joint, RTJ. The steel ring is the gasket. There are different types of RTJs, and basically there are different shapes. There are BX and things like that, but so as not to confuse the issue today, we're just going to talk about the oval type RTJ. This is a gasket like any other and should only be used once. Every gasket that I'm aware of can only be used once. Actually, there is a clamping system that's used in the oil and gas industry, and the manufacturer says that the gasket in that can be used, and the way you check if it can be reused numerous times, and the way you check is you place it in the groove and you rock it. If there's free play or standoff, that gasket can be reused, but it's only in a grey lock clamp, and it's a specific clamp that's used in high pressure applications. The idiosyncrasy is the manufacturer doesn't tell you how many times it can be used. It's up to you to decide whether there is correct standoff. RTJs, like any other gasket, only used once. So, as I said, there are different shapes and different types of RTJ. Raised face. This is the most common, high pressure, and the raised face here is the sealing area of the flange. The gasket sits within the PCD or the BCD if you're from America, the pitch circle diameter or the bolt circle diameter. We should never have to cut a gasket to allow the studs to fit. If we have to cut a gasket, it is the wrong gasket. Okay? We need to check that they call this the stereogram or the phonographic groove. It's very important there's no damage on here or any nicks, because then inevitably the flange will leak. Always check the gasket sealing area. So this is a raised face flange. Now, next one will be a flat face or full face flange. These are for lower pressure, usually on water and things like that, and the whole surface area of the flange is the sealing area, and the gasket will have holes in for the bolts to go through. So, raised face, full face, RTJ. Okay, there are different types of weld necks, different types of flanges, as well as flange faces, and you get weld neck, socket weld, slip-on, composite lap joint flange, and swivel ring flange. All I'm interested in today is the flange faces. Okay, this is more in the realm of for pipe fitters and fabricators and that kind of thing. Now, these are very common in the process industry. This is a flange insulation kit. Every process fluid going down a line generates static electricity, and that is to stop that or insulate from that. These have a special tightening sequence. Please, if you're asked to fit one of these, please observe the manufacturer's fitting instructions, because what you could do, if you put them together incorrectly, you will cause continuity. Okay, so how do we size a flange, or how do we identify a flange and make sure we've got the correct gasket? Well, what we can do is we can measure the OD, or the outside diameter, the ID, and then the PCD, or pitch circle diameter. Look down a chart and it will give us the flange standard, and it will tell us what gasket we need to use from that chart. What we need to be careful of, if we're measuring a blanking flange, we need to make sure that it's the correct material. If we can't identify the material, two different steels will look together, we could look the same, we can create galvanic corrosion. I would say if you can't identify the material, throw it away. Now, so a flange is, how we identify one, is the type and facing, the nominal pipe size, the pressure class, the standard, and if we're lucky, it might say the material and the pipe schedule. So, if we are identifying a flange to get the correct gasket, we would look at the type and the facing. In this instance, it might be a raised face, nominal pipe size, 3 inch, 300 pressure class, ANSI standard. So that would be American National Standards Institute. There are many standards. There are DIN, Deutsche International, GIS, the Japanese standard, SASO, Saudi Arabian, API, American Petroleum Institute. There are lots of different standards. The key thing is we don't bolt two different standards together. So we go back to this. If we identify on the side of our flange, it says RF 3 inch 300 ANSI flange, we can then go to the stores and get a 3 inch 300 ANSI gasket, no issues. What we need to be a little bit careful of is a 300 and a 150 gasket look exactly the same size, except the 300 is slightly thicker. We need to make sure we've got the correct gasket. Often, with fibre gaskets, there are no writing on them. It is only on the original manufacturer's packaging. If you're not sure what gasket you've got, take it back to the stores and make sure you identify it. Nominal pipe size. Pipe is measured by the inside diameter. Tube is measured by the outside diameter. That's the difference. So if it says 3 inch, that is the nominal bore. Pipe is considered a vessel and tube is considered structural. The schedule, if you're lucky, it might say that on it, and that relates to the wall thickness of the pipe. Okay, now when you assemble a flange joint, you need to be careful that you've got the surface, that raised face or flat face, scrupulously clean. You never want to use anything sharp that might damage the surface. You should always use a soft wire brush, or these days you can get really good solvent gasket material cleaners that remove all the residue and don't leave anything on there. They're excellent things. Okay, now types of gaskets. We might get one of these, tanged graphite for high temperature, PTFE or glass-filled PTFE for chemicals, spiral wound gaskets, ring-type joints or RTJs, and that's just another type of ring-type joint. Now, one thing we need to be aware of. Years ago, well up until about 2000, it was possible to get a CAF gasket. That is compressed asbestos fibre. It's very dangerous. It's been banned now since about 2000 in the UK, but there are a lot of gaskets still out there, especially in old installations, still fitted. And the giveaway is, the joint, when it becomes old, it is covered in a white powder. That is an indication that that gasket is asbestos. You need to follow your company procedures. Every company has a different asbestos procedure. It could be that the procedure is wear a mask, wear gloves, take the gasket, put it in a bag, double bag it, and then dispose of it correctly. You then need to dispose of your gloves, your mask, and remove your overalls and get them washed. One spore of it can be very, very dangerous. That has now been replaced by NAF, non-asbestos fibre, formerly compressed asbestos fibre. Okay, so Plunge graphite or graphite high temperature applications. Is this a full face or a raised face gasket then, Ian? That's right. This is a full face gasket because it's got the holes in for the studs to go through. Now Plunge graphite, you have got to be a little bit careful of it because in the middle of it there is a stainless steel mesh to give it rigidity. When they get old, you take them apart, the stainless can go in your fingers and your hands. Please wear gloves. So, glass filled PTFE, these are for acid duty, that would be your corrosion inhibitors, stuff like that. Generally for lower pressures, 300 and below. And then you've got spiral wounds. These things are fantastic things, and these are the ones that you use in CCED. The colour on the outside, that reflects the sealing material, the inner material. Now, every manufacturer uses slightly different colour combinations, and some companies order them in a certain colour. Generally, green is for graphite, for high temperature applications. They seem to be the ones that you use the most in CCED. But you can get blue, yellow, red, etc. Please find out for yourself what your manufacturer uses. And as I said, this one is a Plunge graphite spiral wound gasket, and that material there is graphite. These things are fantastic. You can leave them in service for 5 years, remove the joint, it will leave no residue on the raised face, and they'll always come out in one piece. If you check next time you remove one of these gaskets, you'll find that this area here is very soft. That's the graphite, it's like a pencil. Now, talks about the advantages. We always need to make sure we've got the correct type, pressure class of gasket before we fit it. Just because you've removed a certain type of gasket, it doesn't mean that the last person to fit the gasket has fitted the correct one. Always check that you've got the right gasket according to your procedure. You'll have a different gasket depending on the product that's inside your lines and the pressure class. Okay. Now, remember, any gasket that needs modifying to fit within the PCD of the bolts is the wrong gasket. You'll see it, I've seen it many times. You'll see really elaborate gaskets that have been made and filed out by people on sites. It's the wrong gasket. Please, if it doesn't fit, think there's something wrong. Go back to the stores and get the correct gasket. Now, bolts and fastenings. These are all examples of high tensile fastenings. The one most common you use at CCED is a B7. Now, imagine this is the stud. On the end will be marked B7. When you disassemble the flange, it's really important that you check, do a visual check, that every stud is the same material. Now, that's important because different materials have different properties at different temperature ranges. What might be acceptable at lower temperature might not be at high temperature. All those studs have to be the same material. So, high tensile studs, the one that you seem to use the most is a B7. Now, high tensile nuts. These are all different types of high tensile nut. The most commonly used, and again, the one that you use at CCED is a 2H nut. So, B7 stud, 2H nut. Now, on a high tensile nut, they have a machined surface on one side. It's called an annular ring. And on the outside face, that is where it will be stamped 2H. You must make sure that the annular ring is against the flange face. So here's an example of a high tensile stud. They're generally UNC. You might see them numbered like this, UN8, UN10. I've not come across this before, and it seems to be an idiosyncratic thing they use in a B7 stud. UN8 just means unified course, 8 threads per inch, 8 TPI. UNC or UN10, unified course, 10 threads per inch. Okay, now I want you to consider this. When we tighten a stud or a bolt, it behaves like a spring. If we could measure it, once we've applied the right torque to it, it actually gets longer. It behaves like a spring. If we use it correctly, it will go back to its original length. What we're doing is we're exploiting the mechanical properties of that material, and we're using the stud in its elastic range. If we use one of these things, a flogging spanner, we will damage it and take it outside of its elastic range, and that stud will be permanently deformed. It will be not returned to its original condition. It might not break, but eventually it will. Now, this is what I was talking about. We want to exploit the stud, use the stud in its elastic range. If we use a flogging spanner, we will take it into its plastic range, past its yield point. It might not break, okay, but it will be permanently deformed, and ultimately we'll get up to its UTS, or ultimate tensile strength, and it will break. That is why we use a torque wrench, to keep the stud within its elastic range. Okay? Now, obviously, if we do tighten them up too much, this is what will happen. The bolt will neck and fail. And we've all done this. We've used an incorrect size wrench, or we've over-tightened something, and you can feel it yield, and you know instantly you've damaged that thread. Okay, now, lubrication. Lubrication does a few things in flange integrity, and that is it reduces friction, aids breakout, and stops corrosion. It's very important though, its main job is to reduce friction. Now, when we tighten a nut, if you consider 100% of my effort going in, 50% is lost due to friction at the nut face, 40% is lost due to friction at the threads. Only 10% of my effort going in gets turned into stretching that stud if it's dry. Now, if we use lubrication, that amount of friction comes well down. We reduce it massively. Types of lubricant, these are just some examples. Moly B, nickel 323, EPL, that's basically Vaseline, copper slip, graphite, there are hundreds of them. The key thing is that every lubricant has a different coefficient. Now, if you look at this chart, for a 3/4 diameter bolt, okay, if I want to tighten it up, a dry figure is 559 foot-pounds with no lubrication. If I use Moly lube, the torque figure is 104 foot-pounds. Look at that, 104 with Moly lube, 559 dry. It's nearly 5 times the effort to tighten that stud up dry than if I use Moly lube, because we're reducing the friction. What's important is you take into account your lubrication. If you use a dry torque figure and then use lubricant, you're going to damage the stud. It's very important, or snap it. Okay? Remember, lubrication reduces the friction. It will also massively reduce your torque figure. What you should be doing, if you get a torque figure, you should be asking, is that a dry or a lubricated figure? It should all be in your procedures. Okay. So, we're going to start assembling the flange now. What's really important, if there's a gap between the flanges, we should never use our torque figure to close that gap up. We should always use turfers, ratchet straps, clamps, anything we can get our hands on to pull them flange faces together. If we use our torque figure, we won't be applying that load into compressing that gasket. If you look at this lot, a 6mm gap, if you try and close up a 6mm gap, you'll lose 10% of your torque figure. Always get the joint lined up before you start applying your load to your studs. Now, okay, so we've got our flanges assembled, they're nicely lined up, we've got them parallel. We should use a rule around the circumference of the flanges. Any misalignment a lot of the time there's a lot of clearance on the holes that will reduce the surface area of that gasket. We need to make sure they're as aligned as possible. Then what we do is we set our torque wrench to our first figure. Let's just say our torque wrench, our setting to make it easy, is 90 foot-pounds. Stage 1 we go to 30%, which will be 30 foot-pounds. And we would go stage 1, 1, 2, 3, 4, 5, 6, 7, 8. Crisscross. The correct term is diametric or opposite. I know it's a difficult word, diametric or crisscross. As soon as that torque wrench clicks, we stop immediately. If we go past it, we're putting in more torque. You see this many times. As soon as that torque wrench clicks, stop. Okay. Stage 2, 60%, 60 foot-pounds. Click, 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 click. Stage 2, opposite or diametric. Stage 3, 90 foot-pounds. Again, diametric. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Then stage 4. Stage 4, we go sequentially or all the way round. Excuse me. And that's just to make sure we've not missed one. So we would go click, 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 click. 4 stages. 30%, 60%, 100%, all opposite or diametric. Stage 4, sequentially, all the way around. Okay, so any precautions? We need to make sure we're doing this under payment conditions. We know what the chemical or the product is in the line. Is it hydrocarbon, is it gas, etc.? Is it something toxic? Do we need the correct PPE? Have we got the right tools? What we should do when we break into old equipment or serviceable equipment that's been drained down, remember, we don't take for granted that a line is pressure free and product free. We always think that line is full pressure and full product. We practice safe braking. We never ever undo a flange on a ladder. We should always be above it. And what we should do, if we stand here, we should always brake the furthest away from us. So in this case, we would go 1, 2, 3, 4, 5, 6, etc. What we're trying to do is part that flange and make sure that all the pressure and all the product is diverted away from us. One other critical thing, never remove any fastenings until you can see both sides of that line moving independently. And the reason is, if you took the fastenings out and it turns out to be full pressure, because many times if a flange has been bolted together for a long time, it won't leak immediately. If it does start to leak badly, you can't nip it back up again. Never remove any fastening until you can see both sides of the line moving independently. Okay, so key points. Check all isolations and sign the payment to it. Remember, check the isolations for yourself. Don't rely on the process guy. He might have isolated the wrong piece of equipment. Check on the P&ID. Walk the line. Make sure it's the correct one. Always use the correct tool. Always obtain good position above the flange. Never work off a ladder. Always break away from you. Never remove all the bolts until the seal has been broken. Check the pipe has been supported. There's been many accidents with that. People doing a flange and then a 20-foot length of unsupported heavy flange, heavy line, drops to the floor and damages equipment or hurts people. Always inspect the flange faces for damage before removing any old jointing and reassembly. Refit the new joint of correct material and size. Remember, just because you removed the gasket, it doesn't mean somebody fitted the correct one last time. Now, brief look on tools. We're nearly there now, guys. These are some of the tools that you might use. These are flange splitters. These are good for high pressure flanges or when a line is under tension or been bolted up for a long time. This is a nut splitter. This is a hydraulic one. These are fantastic for removing damaged nuts. Impact gun, remember, only for undoing, never for tightening. These are some torque wrenches. Here we've got an analog one. On this one you turn the handle to set the torque. This is the same, but it's a digital. These are a preset type and will only do one calibrated torque figure. This is a bending beam used for quite precise measurement, like on cylinder heads and things like that. One thing that's very important when we use a torque wrench, we must always ask to see the calibration certificate. If we can't find the calibration certificate or it's not in the box, we shouldn't use it. Also, if there's any damage on the torque wrench, don't use it. Lastly, when we've finished with the torque wrench, we always wind it back to 0 before we put it into storage. If not, we stretch the spring over a period of time and we throw it out of calibration. Always return your torque wrench back to 0 when you're finished. Okay, now this device, I'll just show you this briefly. You might not have seen this. This is a torque multiplier. Now, manually, probably the biggest nut you can tighten up, even with my explosive upper body strength and dynamic charisma and single-minded will to win, the biggest nut I can tighten up is about 1.25 inches, 32 millimeters. These things, they will increase your effort that you put in, and they come in a ratio 5:1, 25:1, 125:1 to increase your effort to enable you to tension large nuts manually. If you get over an 1.25 inches, you should be using a hydraulic torque wrench. These are fantastic things. Now, what you do with these is you have an oil pump where you set a preset pressure. The pressure relates to a torque. You literally just put it on the nut, press the button, click, move to the next one, opposite, click. What you need to be careful of, you don't get your hand in this area here. Low profile ones for restricted access, same thing. These are very good. This is hydraulic tensioning equipment. Remember I told you what we do is we stretch it like a spring manually. These do it hydraulically. So these pre-stretch the stud, and all we do then is flick the nut down and release it. This way we have no friction to overcome. We use these in subsea applications and places like wind farms and things like that. Okay gentlemen, thank you very much. If you've got any questions, please feel free, and thank you for taking part. Good afternoon.